Hi, my name is Sergey Levin, and today I'm going to talk about data-driven reinforcement learning for robotic manipulation. So, the way that AI systems used to work more broadly is that every time we'd have some kind of AI problem to solve, like image segmentation, for example, we would train a specific model to solve that problem. We would train an image segmentation model, a classification model, an image captioning model, maybe a separate model for visual question answering, sentiment analysis, document summarization. Each of these things we would train a separate dedicated model using a separate dedicated labeled dataset. And while machine learning with deep networks worked very well for all of these problems, getting these kinds of systems to work well required large data sets that were labeled with ground truth labels. And that made it very difficult to onboard new problem statements. So while we could get really good image classifiers, it might be comparatively difficult to then adapt those systems to new tasks without having to recollect large data sets again. Now, these days, the way that AI increasingly works is that we start with a very large but weakly labeled data set, and then we train some kind of giant unsupervised or self-supervised pre-trained model, what some folks call a foundation model, which can then be adapted to new tasks with fine-tuning or even few-shot prompting. Now, this is a much more powerful paradigm because a single, very large and diverse data set, or even a collection of data sets that are all weakly labeled, could be adapted to pre-train these powerful representations, and then the resulting foundation models can be adapted relatively efficiently with relatively smaller amounts of data to solve new problems. In fact, while most of you are probably familiar with consolidation across different computer vision tasks or even different tasks in NLP using things like language models, increasingly we're actually also seeing consolidation across modalities with things like multimodal models. This is an example work by Danny Dreiss and colleagues that I was involved with that describes a method that takes a large language model and adapts it to be able to take in images. So if we're seeing this kind of broad consolidation in other areas of machine learning, what about robotics? Well, maybe there's a similar picture here. The way that robotic learning works today is, well, every kind of robotic task and robot might involve a separate model. Maybe you train one model for a PR2 to flip a pancake, another one for a Barrett Wham to flip a pancake, a separate one for UR10 to lift a box, a separate, whatever this is, and so on, right? So every task you have, you collect a data set for your robot and train a policy for that. So perhaps in the future, in the same way that in regular AI problems we have increasing consolidation, we'll see the same kind of consolidation in robotics. Maybe we'll take a large data set of experience from all sorts of different robotic problems and train a giant unsupervised or self-supervised pre-trained robot model, what you might call a robot foundation model, which can then be fine-tuned with a small amount of experience or even few-shot prompted to adapt to new tasks. So what would it take to build such a general-purpose robot model? Well, there are of course a number of challenges. First, we need large data sets to bootstrap our robot foundation models. The data sets used to bootstrap the kind of foundation models we use in computer vision and NLP tend to be very large, and in those domains it's very convenient to harvest the data needed to train those models from the web. Unfortunately, we can't harvest large amounts of robot data from the web, so we need to think carefully about what kind of data we'll use to bootstrap our robot models. Maybe we can take all the things that a robot has experienced in the past, all the different tasks that it's solved, and use that to then pre-train the best possible policy that can initialize new tasks. But we need algorithms that can utilize such data to pre-train these general initializations, and it's not entirely obvious how to do that. Furthermore, once we've done this, it would be really helpful to build on this initialization to allow robots to improve autonomously on the job. So maybe the pre-trained data will be enough to give them a good initialization, but just like in regular recognition problems in AI, the foundation models themselves don't just solve all the problems out of the box. Oftentimes they require some amount of data for the downstream task. And in robotics, it's very natural to get the data on the job from the robot doing what it's supposed to be doing, perhaps even autonomously. And then lastly, these kinds of recipes could help us build up atomic skills, but we still need to then assemble those skills into complete solutions. And especially for things like industrial assembly, the tasks might be complex and very long. So we might need to think hard about how to combine the individual primitives, the individual atomic units that we get from this kind of large-scale pre-training into complex multi-stage tasks like cable routing. So in this talk, I'll really talk about the puzzle pieces that might constitute a future robotic foundation model. I don't have a single kind of solution that I'm offering, but I'm going to talk about a variety of projects that we've done recently that I think illustrate what the individual puzzle pieces might look like that we could eventually put together into a general pre-training recipe in robotics. I'll talk about bootstrapping with large data sets and where those data sets might come from. I'll talk about pre-training with offline RL, and then I'll talk about training autonomously on the job and discuss a few case studies of where we've done this. And then I'll conclude with a discussion of hierarchical learning and assembling the primitives into complex behaviors. So can we pre-train robots with large data sets just like we pre-train foundation models in other domains? Well, the first thing we need, of course, is the data set. And ideally, we would have a data set of all the things that the robot has experienced in the past, so that when you get a new robot in your particular domain and you want it to learn particular tasks, you've got the data necessary to initialize this. So one of the things we've been doing over the past few years is actually collecting such data sets. My own take on this is that once robotic learning really takes off, once it's used across the board, this will be a lot less of an issue because we'll have data coming in from robots in all sorts of settings. But to get this process started, we need to provide the activation energy, and for that we need to bootstrap with data sets that we collect ourselves. So we've collected a data set called the bridge data set, which is really aimed to bridge the generalization gap between a new domain and a large collection of prior skills. So it's supposed to provide, essentially emulate the setting where you have many different behaviors that the robot has already done that can be used to then bootstrap some new task. We recently released version 2 of the bridge data set, which is collected entirely with a single robot. It's a low-cost robotic arm called the Widow X arm, but it is collected in many different environments and contains 54,000 demonstration trajectories across a huge range of tasks. There are hundreds of objects, full language annotations for each one, and 24 different environments. By including a variety of different environments, we hope to make it possible for other researchers to train policies on the bridge dataset and either transfer them to their own setting or at least fine-tune them to their setting. And in fact, we've confirmed that policies trained on the bridge dataset can run in other institutions using similar kinds of tasks. Here are a few examples of the tasks and policies in version 2 of the bridge dataset. These are goal condition tasks. These are being performed by a goal condition diffusion policy. And you can see here on the left is the goal image specified to the robot, and on the right is a sequence showing the execution of the robot. And so you can see it can execute some fairly complex tasks like sweeping objects and folding cloth. Here are some examples of language condition policies trained on the bridge dataset. Here, the string on the left is provided as an input to the policy. So this is actually the RT1 policy from Google adapted to run on the bridge dataset. So hopefully these kinds of data sets, while they might not enable the robot to perform the particular tasks you want, they might provide a general initialization that can make it very efficient for you to train the robot to perform the task you want. So let's talk about that next. Let's talk about the kinds of algorithms that could utilize data sets of this sort to perform diverse tasks with limited amounts of data. So what kind of algorithms could we imagine using? Well, we could imagine using imitation learning algorithms. That's pretty straightforward. If you have data of the robot actually performing the task that you want, you could fine-tune from a multitask initialization. But another very appealing possibility is to use offline reinforcement learning algorithms. So these algorithms would actually utilize the data without necessarily assuming that it's optimal for the task you want to solve. So they might recombine parts of the data to learn a policy that is better for the particular new task, even if the data doesn't actually illustrate optimal executions of that task. If we use reinforcement learning, we of course need to define the task somehow. We could define it with one-hot vectors and hand-designed reward functions. In fact, that's what we're actually doing in some of the experiments that I'll show later. But we could also define tasks with instructions or even image goals. And all of these are very reasonable strategies. In fact, image goals are a very appealing option if you want very general purpose pre-training objectives because they don't require additional reward engineering. But let's talk about some experiments to examine whether pre-training, in this case with offline RL, can actually boost the efficiency of downstream skill learning. So I'm going to talk about a work that we did at this point about a year ago called Pretraining for Robots, or PTR, which uses an offline RL algorithm called CQL to pre-train on version 1 of the bridge dataset. Back then the bridge dataset was smaller, it was about 10,000 demonstrations, and then studies fine-tuning of these offline RL pre-trained policies to new tasks with just on the order of 10 trials for that task. So this is a largely experimental work. The setup is actually very simple. For every task, we have a one-hot vector that tells the policy which task it's supposed to be doing. And the last entry in that one-hot vector is reserved for the new task the robot will be fine-tuned to. We train a single policy on version 1 of the bridge data, which had about 100 tasks and 12,000 demonstrations. And then we take this pre-trained multitask policy, we give it 10 trials of a new task that is structurally similar to the previous tasks, but it might involve new objects in a new environment, and directly fine-tune it with the same offline RL algorithm. And that gets us some policy for that downstream task. So there are a number of experiments in the paper, but I'll tell you about one set of experiments which specifically deals with new tasks in new environments. So this is meant to be most representative of what happens if you actually want to use the bridge dataset to learn a particular new task with your own robot without having to collect a large data set of your own. So in this case, there are 4 new tasks. They're structurally similar to the tasks seen before. They're all kind of pick and place style tasks, but they're in a new environment and they involve new objects. The performance of PTR is shown in the column on the left, and there's comparisons to other methods that use other kinds of pre-training or don't use pre-training at all. Now, all of these methods are far from perfect, but PTR does get the best result, still around 50% for most of the tasks, so definitely plenty of room for improvement. But a particularly interesting comparison that I want to draw your attention to is the one shown on the far right. So here we're comparing 2 previous representation learning methods that you can think of roughly as computer vision techniques. These are techniques that were proposed to learn visual representations from large and diverse data sets, but that don't necessarily learn policies. So you can see that these methods perform a lot worse than PTR, and this really illustrates that pre-training on diverse robot data with offline RL in particular, meaning pre-training for maximally optimal behavior at actually performing the given tasks, results in better downstream fine-tuning than merely pre-training visual representations as if we were to train more conventional computer vision style foundation models. So this is really important because it suggests that training robotic foundation models with RL-based algorithms will lead to significantly better fine-tuning performance. In fact, we see that as we increase the size of the model, as shown in the graph, all the way from a small ConvNet to a ResNet 50, the performance on the downstream fine-tuning tasks continues to improve. We've recently extended this system to accommodate pre-training from video data. So in this case, we can actually develop RL algorithms that can train not policies, because video data doesn't have actions, but they can train state value functions on videos of humans performing tasks, in this case gathered from the Ego4D dataset. And that provides a value function which can be used to initialize the Q function that we then train in stage 2 on the RoboNet dataset, and that then provides an initialization that we can learn individual tasks in stage 3. So the video data is not used to pre-train the policies, but it is used to pre-train value functions, and that greatly accelerates downstream learning. We've confirmed that this greatly helps with generalization, particularly in the presence of distractors. So these tasks are a little different from the ones in the previous experiment. They're harder because there are more distractor objects in the scene. And you can see that in this case, V-PTR, which is PTR that includes the video data, does decently well, still far from perfect. And interesting comparisons here are in the 2 rightmost columns. So the second from the right, that's regular PTR. And the rightmost, and that's the one I think is most interesting, is the one where we skip phase 2. So we use video data and we use a small number of trials from the downstream task, but we do not use the bridge data set. Now this is a lot worse than the full V-PTR method, but it's actually the second best baseline, which suggests that this method really extracts a lot of useful, actionable information from that video data. That information is further improved significantly by using robot data, but in fact it's actually the video data that gives the bulk of the generalization improvement. Okay, so that was all about using diverse robot data to pre-train offline and then do a little bit of fine-tuning with a small number of trials. But a really powerful thing that we can enable with robotic learning that's actually unique to robots, that is maybe not the case in other areas of machine learning, is the ability to further improve autonomously. So there's a lot of power in being able to autonomously improve on the job after initializing from one of these diverse pre-trained models. Because we won't ever be able to build robots that never make mistakes. I think that's too high of a bar, but perhaps we can build robots that can learn from their mistakes and then get better and better. And if they can learn while doing the job that they're supposed to be doing, then essentially the robots will get better the longer they're deployed. So if machine learning is bottlenecked by data, robots that collect their own data will be the most powerful ML systems imaginable, because the longer they run, the better they get. So how do you get robots to learn without human intervention after initializing them in this way? Well, let's use a little thought exercise to illustrate how this might work. Let's say that you want a robot that will use a coffee machine to make coffee. Maybe you have a task that you're going to give the robot to learn, which is to put the cup in the coffee machine. And maybe the robot will mess up and it will drop the cup. Now at this point, a person could come in and reset the environment so that the robot could try again. But maybe if you want the robot to learn autonomously on the job, this is in fact an opportunity for the robot to learn a different task, the task of picking up the cup. So you have task 1. If you fail at task 1, then you try task 2. If you succeed at task 1, maybe now you have to put the cup back, and if you fail at that and you spill the coffee, maybe that's your opportunity to practice cleaning up the spill. So what this illustrates is that multitask learning is a very natural fit for enabling autonomous learning on the job. Here's an experiment that we did a couple years ago that studies this. Here the goal was to get a robot to learn to pick up an object and reorient it in the hand. But the goal was to really to train this task fully autonomously. If the robot drops the object, there's supposed to be another task that it can practice from that position. So we had 4 tasks: lifting the object, recentering it in the bin, reorienting it in the hand, and flipping it right side up in the hand. And we created a graph of how these tasks relate to one another. So if you fail at in-hand reorientation, you drop the object, now you should recenter it in the bin and then lift it again. So each of these tasks essentially resets some other tasks, and together they create a network where for every state that the robot might find itself in, there's some task for it to practice. And using this setup, we can actually get the robot to learn this entire task from scratch in this case with online RL. It takes about 60 hours, but it's fully autonomous. So here we're showing this fast forward. We turn on the robot, the student goes home to do some homework, and the robot trains. And it learns all these tasks simultaneously, learning, lifting, recentering, and reorientation. And at the end of this training process, it can successfully perform the entire task. So I think this gives us a recipe, a sense of what fully autonomous robotic training in the real world might look like. More recently, we've extended the system to incorporate vision and actually start experimenting with the use of prior data. So here we're going to have, again, a network of tasks, resetting, picking up the object in hand, and then repositioning it in the hand. But the idea now is that a new object will have its replay buffer initialized with data from other objects, and maybe even other poses from the same object. So maybe if you've learned to reorient the pipe, that will help you reorient the football. So that's the setup. This is the training procedure for the first task in the sequence. This one is actually learned from scratch. This is to reorient this 3-prong object. Unlike the previous experiment, which used motion capture, this one is done entirely from images. The reward is actually specified with an image classifier, and the entire training process takes on the order of about, I think, 7 hours. So it's actually gotten quite a bit faster from before through improvements in the core RL algorithm. But once we train this 3-prong object, this is the in-hand reorientation video, then we can initialize the buffer and use that to train a different object, in this case the pipe. Now you'll notice these objects are actually very different, so it's not at all obvious that learning to reorient that 3-prong object actually helps with the pipe. This is learned from pixels, so the robot needs to understand that the visual appearance of these things, that the colors don't matter, but the shapes do matter. It needs to learn to pay attention to the fingers. But we actually find a speed up of over 2x on most of these objects from initializing the buffer from other objects. So that's actually pretty interesting. Now, this is a very small scale experiment in the sense that for each of these tasks, it's initialized from one other task. Of course, in reality, we might initialize from some large data set of past experience, and perhaps there we'll see even more improvement from this kind of autonomous training. On the topic of autonomous training, another experiment I want to tell you about is some work that we recently completed at Google Research that tries to scale up robotic RL for tasks that are much more applicable to the real world. So the particular task that we want to address is the task of sorting recyclables, where a robot approaches a trash bin and sorts cans, compostables, and trash into corresponding bins with reinforcement learning. Now, at its core, this is really a bin picking problem, although the robot does have to decide which bin to place the object into, so the policy is actually end-to-end in this case. And the training involves reinforcement learning with some degree of autonomy and some degree of real-world deployment. And I think that while the previous project illustrates how to make a system that is fully autonomous, this system is not fully autonomous, it does involve some human intervention. This project does illustrate what a learning-on-the-job pipeline at scale for a real industrial task might look like. So the system is bootstrapped with a crude scripted policy that can collect some initial data in simulation and in classroom environments. And then it trains further from actually sorting at 30 different waste sorting stations across 3 real buildings populated by real people, in this case, Google employees. So this is what the classrooms look like. This is essentially what the robots use to bootstrap their experience, where they continuously sort trash in these preset settings. But at the same time, other robots are also navigating real-world environments. They're pooling all their experience and getting better and better at real tasks. And in the end, this thing could achieve success rates of over 80% in actually picking up the trash from the bins. It was very diverse. Humans deposited all sorts of different items into these bins. So this was actually like a fairly complex experiment to do, and there was actually quantifiable benefit from collecting data in the real-world deployment environments, from actually learning on the job. Okay, so that was about how to get the core robotic skills, but the last thing I want to talk about in this talk is how we can then take those skills and assemble them into more complex and compound behaviors. So what if we have larger multi-stage tasks? We can learn individual primitives for things like picking and routing and manipulating objects, but perhaps smartly sequencing enough of these skills can actually enable powerful multi-stage robotic skills, and being able to sequence the skills intelligently could actually make longer tasks easier. So the trouble is that if we have some compound task, like for example, routing these cables, we could simply deploy the individual skills like picking up the cable, slotting into the clip, and so on, sequentially. We could say like insert clip 1, move to clip 2, insert clip 2, move to clip 3, insert clip 3. The trouble is that the more stages there are, the more the probability of failure compounds. If every stage has an epsilon probability of failure, then we're going to go up exponentially with the number of steps in terms of our probability of failing overall. So if we have a variety of skills, what we can do instead is we can be smart about deploying those skills to correct potential mistakes. So the way that the system is going to work is we're going to have a bank of skills. Some of them are learned and some of them are hand designed. And we'll have a higher level policy that actually chooses which skill to deploy next, depending on the state of the system. So this video is going to show the skills. There's a routing skill which actually inserts the cable into the clip. There is a pickup skill which picks up the cable at a particular point. There's a perturb skill which randomly moves the cable. And then there's a command for the higher level policy to move on to the next clip. But crucially, the policy is going to look at the image and decide which skill to deploy, and that allows it to fix mistakes. So here's the complete execution, and you can see the visualization in the top left shows what the higher level policy is deciding. So here it chooses to execute the route primitive, which tries to insert the cable into the clip, and on the first clip it actually succeeds. So it moves on to the second one. For the second one, it will attempt to route it, but it will actually fail. So now it will deploy the perturb skill, which just performs a random perturbation. In this case, it just so happens that the perturb skill happens to slot the cable into the clip. It might not have done that, in which case it would need to perturb again. So then it moves on to the next clip and routes that. Each individual routing primitive might have a pretty high chance of failure, but because the higher level policy is smart and corrects those failures, the overall success rate is actually very high. Now, here the higher level policy was learned specifically to, with imitation learning in that case, to deploy these individual primitives, but we could also use semantics to automatically obtain much more intelligent higher level policies. So this is some work that we did at Google where we first trained a language conditioning policy for low-level primitives. This is a policy called RT1, the robotics transformer, and it can perform, roughly speaking, a wide variety of atomic kitchen-style tasks like picking up objects, opening drawers, that sort of thing. And then we trained a multimodal language model, a language model that takes in text and image observations and outputs responses to questions. And it can answer questions about images like describe what's going on in this picture, but it can also answer questions about robotics problems. Now, it doesn't actually take robot actions, it answers those questions with text. So if you ask it, how do you grasp the blue block? And it can see that the blue block is lying underneath the yellow block, then we'll say, well, first grasp the yellow block, get it out of the way, then pick up the blue block. Now, by itself, this doesn't actually allow the robot to perform the task, but connected to the RT1 model, now we have a complete robotic system because this PaLMi model, this language model, can command the skills in language, and then the RT1 model can perform the individual atomic skills. And with this, by connecting PaLMi to RT1, we can actually enable the same kind of corrective behavior that we saw before with cable routing, except that now it's enabled through generalization. It's enabled through the language model using all the prior knowledge learned from internet scale data to generalize to whatever situation the robot encounters. So here, PaLMi is told to pick up the chips. It commands the robot to open the drawer, and then it commands it to pick up the chip bag. And when it receives a perturbation, PaLMi knows that the chip bag is back in the drawer, so it again commands the robot to pick up the chips, because it's observing the image and commanding the RT1 model. Here's an illustration on simpler tasks that gives some insight into the sorts of commands that PaLMi issues. So here the task is to sort the colors into corners, and PaLMi looks at the image and says, push the red circle to the red star. Then it says, push the yellow heart to the top right corner. So knowing which command to issue, of course, requires PaLMi to see the image. But otherwise, it can leverage the rich semantics it learned from internet scale data to figure out which commands to issue to the robot. And as long as the robot has the atomic skills learned with these robotic foundation models to perform the individual steps, then the entire compound task can succeed. All right, so to summarize, I talked about these problems that we need to overcome to enable real robotic foundation models, and I talked about some of the puzzle pieces that might help us make this happen in the future, like bootstrapping with large datasets, pretraining with offline RL, training autonomously on the job, and assembling complex behaviors. I think that these steps can bring us closer to a future where we can pool all of the robotic experience that we've gathered into one giant dataset, train a general purpose robotic foundation model, and then fine-tune it or even few-shot prompt it to perform particular downstream tasks. I'd like to thank all of my colleagues, my students, my colleagues at Google that carried out this research, and I'd like to thank you for listening.